Yes, I can record, sorry. And a lot of applies to other types of motors, but basically look at what are the pieces of the motor specification that we need to pay the most attention to as we are designing electronics for these things. In this course, our main focus, I said lots of time, motor control and motor control circuit and motor control techniques. We have three main targets. Okay, so I won't spend too much time on the general course agenda, but let's take a look at the types of motors we might be talking about. And the electric motors, you know, is very wide-ranging field. Maybe after last week course, you can search from the Google, etc. Generally, in vehicle, I said you nearly more than 200 electric machine in one traditional vehicle. In your home, refrigerator, etc. I said you. Okay. So motor is important for electrical engineering and mechatronics engineering. So we are going to be mostly looking at the DC motors. So not AC motors that plug into the wall or run from the mains. But everything here I'm talking about is going to be a rotary motors. Also, don't forget it, we have no rotary motors. We have linear motors. Okay, two types of motors, some of them rotational, some of them linear. It's another aspect of the discourse. While there are, and I will just, as an aside, there they are on the side talking about linear motors that could run along a track or solenoids or piezo. There is certainly specialty application where we might see those in this course. But in general, I'm going to focus in on the DC motors today. And they fall into a couple of different categories. Those that have brush and those that don't. And stepper, well, you might consider them a brushless motor because there are not any brush in stepper motor. And we will bring them all up, but that will be what we find in automotive separately from AC motors. And by the way, you will see some notes at the bottom here where we are talking about the various reference in the slides. Maybe you can visit that website. Generally, we can benefit from the some motor company manufacturers, some cheap productor, etc. This is very really just be a quick overview of this. In your screen, you can see electric machine, one of type rotary, another red blocks, linear. Also, we have two types, DC and AC motors. Okay, DC motors have two categories, brush DC, brushless DC, and also AC, induction motor and PMSM motor. PMSM motor is meaning that permanent magnet synchronous machine. Why we can use a machine terminology for electric motors? Because machine is meaning that motor generate mechanical energy from electrical to mechanical. However, a motor we can use as a generator from electric to mechanical or electric. For example, wind turbine. For example, regenerative braking in electric vehicle. That's what motor is meaning that from electrical to mechanical. Machine is meaning that we have two capabilities from mechanical to electrical, from electrical to mechanical. Okay, this is important differences actually. Maybe after that we can use machine terminology sometimes. Okay, now basically we will break them down into brush DC, which we will talk about in this segment, but there is also stepper which don't have brush, I said you, and nomenclature of those brushless DC implies a different thing than stepper and mostly has to do with the construction and operation of those. But neither of those has brush. But when we talk about BLDC, BLDC is meaning that brushless DC motors or machine We are typically talking about three-phase brushless DC motors. Where brushed, the subject we will talk about today, are the simplest and easiest to operate and have some different advantage. Next week we're gonna talk about the brushless DC machine. But we find all three of these motors throughout all kinds of automotive and consumer electronic and aerospace applications. So we will talk a little bit about the application in later part. And just I will propose some microcontrollers, some circuit schema, etc. And then typically for the types of motors we will talk about, there is also permanent magnet. What is the permanent magnet? So we are going to make an electromagnet that we can control by the current. There is going to be existing someplace in the motor also permanent magnets. Maybe after the course you can search in the internet what is the permanent magnet, neodymium permanent magnet. Probably you will see some motor material as a permanent magnet. And those are of course going to push against each other. So if we have a north pole and the south pole, they are going to the repel. Generally, bachelor students focus three types of motor. Actually, we have lots of advanced motor system. For example, servo motor application, PMSM. For example, induction machine or asynchronous machine. For example, synchronous machine. Or generally, in the bachelor education, we are focused brush DC, stepper motor, and brushless DC. Brushless DC main specialist is high power, high torque. Stepper motor controllability, current control needed in this book. Actually, main advantage of stepper motor, it's open loop. What's the open loop? What's the closed loop? If you need a feedback from current, from speed, from voltage, etc., this is meaning that closed loop. If you can use closed loop system, you need to develop a controller, such as PID controller, such as PI controllers, such as ANM, fuzzy logic, etc. We have lots of control algorithm. Also, basically, brush. What's the advantage of brush? Low cost, easy to use. But we have lots of advantage. EMI, VROT, noisy, maintenance, etc. But for example, brush DC motor, for example, just a $10 stepper motor. I suppose that $15 brushless DC motor, $40. It's very expensive, but we can use brushless motor in electric vehicle, in lots of high technological products. Okay. Uh, Good. So it can turn the motor on, turn the motor off. Now, yes, what's the main idea of the DC machine? Maybe you can remember from your course. Which course? Which course? Electromagnetic theory. In electromagnetic theory, you see some law, like a like a this one, for example, Ørsted, for example, Maxwell law, etc. Actually, main philosophy of the motor definition, motor law definition, you need to turn to electromagnetic design course. Why? Because you remember Maxwell and Tesla is the main researcher and scientist of the DC and AC machines. If you want to learn lots of parts electric machine, you need to turn your electromagnetic nodes. It's good because, for example, in this website, it's just a simple remember slides. You can see electric currents create a magnetic field. We have a wire, we have a B magnetic field, we can generate current. This is important. So maybe we can see right side of the screen. It's the opposite magnetic poles, north and south. Typically, one pole pair, two pole DC machine. It's interesting. Why? Because here you can see brush. These are brush. Okay. We want to control electromagnetic field using brush. We have plus and minus, you can see, but we need sinusoidal voltage in our magnet, like this one. North, pole, north, pole. This is actually typically sinusoidal. Why we can use brush? Brush, for example, in mm, we have a DC signal. Okay, brush converted positive alternance, and then brush must turn to the negative side. Actually, our main voltage same. For example, we can use battery supply direct current and direct voltage. So my brush act as a positive alternance, and in this point, after 180 degree, he turns minus side. This is cancelled. My waveform goes to minus alternance, like this one. This is like a sinusoidal operation. But and then in the next slide, basic DC motor driver topology. This is important for us. Generally, in our life, we can buy from market a DC motor, and then we want to operate it. So we need half bridge, full bridge, and three-phase controller topologies. Now, here at the here at Okan University, for example, we are interested with the electric vehicle, etc., in control and driving of these motors. So we want to have some topologies. So we talk about the motor drive topologies. I will refer to half bridge or full bridge or three phase, and these are various types of turning on switches. You can remember from power electronic course, semiconductor switch. In your screen, you are seeing MOSFET as a switch. And these diagrams, what we can see is that there are field effect transistor, MOSFET, IGBT, which is one way to do switch. But a half bridge, basically, you can drive a single brush motor in single direction. If you design half bridge, you can control brush DC machine one direction. Okay, only your motor rotate only clockwise or counterclockwise, only one direction, because we are using two switching components. Three modes: run, coasting, and braking. Good. Probably in your one homework next days you will design half bridge and full bridge and three phase. First of all, half bridge now. So it can turn the motor on, turn the motor off, but is not reversible. So we'll talk about the different mode, but there is the running mode, and certainly there is an off mode. It's not really operational, and then we can also coast or we can brake, and we will talk about that a little bit differently too. Now I compare that to a full bridge, and I avoid the use of H bridge, which is sometimes a nomenclature for a full bridge. Full bridge and H bridge is nearly the same thing. And you can see in this second middle diagram where you can sort of see the H that forms around the motor. We are in here, full bridge. But I have seen confusion between a half bridge, which starts with the letter H, and the full bridge, which is sometimes called an H bridge. Don't confuse it. H bridge meaning that full bridge. Half bridge is a very simple circuit. So I will stick to the half bridge and full bridge nomenclature. And what we can do with the full bridge, we can't do with the half bridge is we can drive the motor is in one direction by turning on this transistor at the top and this transistor at the bottom and have current flow through that motor. Or we can turn on this one and this one and have current flow in the opposite direction here. For example, here this half bridge operation, only one direction. Also in full bridge topology, we have return like this one. It's the another direction. Here we have only one. Okay. Uh, we will see if you look at a stepper, it basically is made up of two full bridges. Actually, step motor is more complexity circuit diagram, not this one. Two full bridge combination is meaning that stepper motor driver. So it's just an extension of this one, full bridge. And if you look at a three phase, it's really made up of three half bridge. My favorite every time, three phase, because it's a commercial, it's a industrial, etc. But because there are three phase of brushless, typical three phase brushless brush DC winding, if you can design a three phase, probably you can use BLDC machine. If you are use half bridge, you can you want to control DC motor with only one direction. If you can design full bridge, you will control DC motor with all operation mode, clockwise, counterclockwise, regeneration, etc. If you have two full bridge, you will control a stepper motor. Okay, half bridge for one direction DC machine control, full bridge two direction DC machine control, two full bridge. You want to control stepper motor. If you design three phase circuit, you want to control BLDC motor. Okay. Okay, so a little bit of that behind us. That's the drive stage for getting the current to go through and creating these electromagnets that then create a force or torque that we need to make this thing spin and drive a load. So all of this very generic in terms of all these system, but then beyond the motor drive, as far as electronics, we will also need a microcontroller of some kind. Okay, typically that will make the decision based on, well, what's my desired motion? What is my speed right now? What position have I have achieved? So all that information coming back, there will be typically and especially in consumer electronic, automotive electronic application, communication to other parts of the vehicle or home, smart home communication parts, etc. And then, because we don't necessarily run all these electronics directly from the battery, there is typically some part of power supply that will convert from raw power to whatever is needed for all these various electronic pieces. So regardless, and this applies to motors throughout the vehicle, for example, as well as just about every other motor that's used. Some of these components will be obviously available in all sorts of application. Now we are focused the DC machine, brush DC machine. They are simple and inexpensive. We see them throughout all sort of the vehicle, consumer electronics, individual, all robotic application. But brush motor are used pretty much wherever you need reliable operation and simple electronics is really all that's need. Okay, now in your screen you can see typical model of our controller in this system. Typical electric drives. We have power supply, we have controller, we have communication part, we have position sensor, we have speed sensor, we have motor drive circuit, full bridge for example. This is your DC machine, this is your gear and load. Okay, this is the simplified parts of electric drive, simple electric drive system. If you want to design a very simple, for example, toy vehicle, autonomous toy vehicle or autonomous electric vehicle as a toy, you need to design these parts. You need power supply, you need microcontroller, you need communication, for example, serial communication, CAN bus communication, flex ray, etc. Also, you need to design a motor drive circuit, like a half bridge, very simple, a four switch for MOSFET, for example. Also, MOSFET driver, and then we need position sensor. What's the position sensor? Hall sensor, encoder, resolver, etc. And then speed sensor, like the position sensor actually. You know the integration, sorry, out loop of speed. For example, if you detect the speed, you can integrate it with the 1 over s, the speed, you obtain position. Okay, speed and position is a relation, you know. Yes. Now, full bridge normal operation. Why is the full bridge normal operation? Actually, it's important for us because all electric machine start with the H bridge. So full bridge normal operation. Please focus to your screen. We have only 20 seconds focusing. We are silent. This website very important. Okay, I think everything, every students understand the operation. Okay, so we are going to take a look at various pieces of motor drive, and here in this diagram, this represents the winding. Okay, I said to you, this is the parts of winding. So a winding that's going to create the electromagnet also has typically a significant conductance. So we have to keep track of the motor parameters that go into the electronic characteristic of the motor. So we will have switch. Okay, this is critical. Now, this could historically has often been relays, like a relays, on off, on off, on off. But if we want a full bridge with intelligence and better control, we are typically going to be able to replace relays with transistor of some type, typically a power MOSFET, depending on the size of the motor. Okay, So we see a forward direction. If we turn on the phase A, okay, the high side MOSFET going to get current from the battery or whatever the filtered power might be goes through the motor, creating a torque in one direction, and then returns back to the ground through the B phase low side field effect transistor. This operation is very critical. It's seen easy, but it's the main philosophy of the motor control techniques. That would be, we can call this forward. Might be up, might be down, might be open, might be closed. Whatever the motion is, it will tend to create a torque in one direction, and cause motion. For the opposite, we are going to turn on this B phase, high side MOSFET, and the A phase, low side MOSFET. So this is the general operation of full bridge drive. And notice, we will never want to turn on both the high and the low phases, which would create a direct path from battery to ground and the very high current path. So we need to do things, and this comes in part of the intelligence of what we have to do with the motor drives will be to make sure that as we switch from this to this, from the high side to the low side being on, that there is what's typically called a dead time, place where both have to be turned off so that we don't get what's called shoot through current. What's the shoot through? Shoot through is meaning that we don't want to open at the same time a H and a low, high side, low side. B switching low side, high side is called as a high side, is called as a low side. If the high side transistor and the low side transistor operates at the same time, this is called as a shoot through, short circuit. Okay. For example, on position. This is the short circuit. If we have a short circuit, your circuit will be the match. For prevent this one, we can add dead time. For example, a high side MOSFET goes to low side MOSFET goes to high side. We have a time. This time is called as a dead time. Okay. So if you think about the motor is going to do, it's going to spin, it's going to have a certain speed. If there is a load, there's going to be a torque. This in your screen you can see typical speed torque curve. This is the classical speed torque curve of DC machine. In the y-axis we have torque. Generally we are using Newton meter unit or Oz in unit in Europe, Oz in generally in US, Newton meter in generally Europe. Also speed. Speed meaning that rotational speed of your electric machine. As a mechanically we can use RPM. RPM is meaning that revolution per minute. Okay, this is the typically definition of speed torque curve. Now, here a critical point. Generally, all students think that our motor have no load. Actually, if your motor rotate as a only individual, as a only rotate individual, it's no load operation, no load. No load and load is different thing. If you connect with using a couple with another rotational load, this meaning a full load or medium load, etc. Okay, please aware of the full load, no load, half load. It's important. For example, no load speed is different, loading speed is different. If and the brush motor have very typical torque speed curves actually. It's very easy. You can see in your screen. Speed is goes up, torque is goes down. It's very easy. For example, in PMSM, in the synchron machine, in induction machine, speed torque curve is very different from DC machine. So they are linear, you can see they are linear in terms of the trade-off between the torque and the speed and the two endpoints you can see, and each of these will be, by the way, each curve would represent different applied voltage. This different curve indicates voltage. For example, here it's just my idea, 12 voltage. For example, this one, 24. This is, for example, 36. This is, for example, 48 volt. Okay. Generally, DC motors operates the different voltage level. So, for example, if an automotive application, we might have 12 volt supply voltage, and so we would be seeing the motor characteristic along this curve, and maybe if it was truck or something with a 24 volt, for example, you know, classical traditional vehicle, generally we are using 12 volt. In the truck, etc., we are using 24 volt. We might have a high torque and higher speed curve in truck because our voltage level goes up to high, and then we can see high power, high speed curve. And perhaps at the lower voltage, for some reason, we will have different torque and speed curves. But the two endpoints of the operation in speed torque curve, two endpoints of the operation will zero speed. Zero speed, we have a maximum torque in DC motor. If you are in zero speed, you have maximum torque. It's critical. So we get a maximum torque when we are not moving at all, and that's where, if the load is not using up all the torque, that's where we get the most acceleration. So we accelerate, and as the speed increases, the torque comes down. So if you think about, if I turn on the motor, what's going to happen? Is it going to start up and it's going to spin faster and faster? It will change along this torque speed curve until it gets to its no load speed. So here is our no load speed, which is in this case about 5,000 revolution per minute, and that is the fastest that the motor will run, assuming that it's not driving any load. Now there is internal, and this is the one of the characteristic of brush motors. There is brush drag, and there is friction of the bearings and all the things that go into the internal torques. But this is talking about the shaft torque, that says if there is no externally applied torque, I am going to have a maximum speed. Conversely, at the other end of the spectrum, if if I increase the torque, so if the load torque on the shaft increases, my speed is going to decrease, and at some point when I reach a maximum torque, I will actually stall or reach stall condition. Stall condition is very important. We have torque is a maximum at zero speed. This meaning that stall torque, maximum torque at zero speed. It's called as a stall condition, and that is the stall torque where the maximum amount of current, rather than producing a speed, will produce high torque. Okay, so anyway, you go back and forth between these two endpoints. And notice, of course, that if you are talking about the useful power, like you can see in your right side of your screen, which is what we really want to do for driving a load. Maximum power at middle of curve generally. Okay. It's not driving any motion, so the motor just by itself is not a particularly useful thing to happen. And the other end, well, if it's pushing but it's not rotating, that's really not doing me any good either. So my efficiency is zero at both endpoints, and power efficiency is the highest somewhere in the middle, and will always operate if we want to get motion someplace in the middle. Although we will have to transition through to zero speed, certainly as we start up the motor. Okay, so we are going to see this is a parameter of the motor that basically tell us what's the speed available from the motor. Okay, now if we get into a simplified motor model, main focus, we will develop this model using MATLAB. Today we just start. Next week we will focus details of the simplified motor model. We want to understand it. It's very important. Okay, well, we are going to apply a voltage to it. My main input voltage in DC machine. We are going to get a current through heat. You can apply a voltage, we obtain current. How does that turn into motion? What can I expect as far as torque? What are all different aspects of these that are going to work? All right, so this is the simplified potentiometer. Yes, what we see here is we have got a voltage, the applied voltage here at the input. And then everything, the load itself might be included as part of the mechanical. This side of electrical modeling, simple electrical modeling. This is simple mechanical modeling. We have two models in a DC machine. And this is a model of the electromechanic action of the motor. All right, so we will look at the pieces in these. And we have a coil of wire, so it has an inductance, you know, and that is the inductance to the motor right there. This is winding inductance. This is winding resistance. In my DC motor model, we have very simple. We have resistance, also inductance, also we have back EMF. This is just a simple DC motor electrical model. This is my resistance, inductance, and back EMF. So, and the motor current, no, mechanical energy, okay, we say something about it. So, there is geometry here, as well as the material properties, but we get a torque constant, or motor torque constant, Km. This is called as a motor torque constant. I will say something about it as a detail. This critical parameter. Also, I check. Maybe we can say torque constant say us per ampere how much torque in Newton meter. So this turns into a motor torque. So the motor torque will then becomes a mechanical rotational wheel being some rotation, but rotation the speed, and this will turn into acceleration. Depends on a couple of things. One is the friction. This is we have a friction parameter, viscous friction, Bm. Motor inertia, you know actually. This is motor torque. Drag torque is actually noise load torque. This is TD is load torque. I generate mechanical torque. This is load torque. Mechanical torque minus load torque. It gives us main load. Okay, that's good. Uh, we have a motor model, mechanical and time constant. Okay, this is the good starting. I think for today is enough. We can continue next week. Tomorrow, please come to class. How many students? Yes, we have 10 students. Okay, we can finish today. Please download MATLAB. Next week, we will continue with the MATLAB, etc. Okay, maybe we can uh, 1 plus alpha hour course next week. I will upload my slides. Don't worry about it. I will send you in Learn. If you have no question, we can complete the course today. Do you have question? I suppose that you have no question. Okay, we can complete. Actually, faculty elective course on Saturday, 1 hour. Don't forget it because lots of students have lots of faculty course. It's interesting, 1 hour, but after this course, some students have a course, engineering management, technology management, etc. So we have only 1 hour in this course, but we can complete it all subject. Thank you for attendance. See you next week, dear all. Please download MATLAB Simulink. Okay, thank you. Bye bye.